All right, so welcome back. Uh, this is the ninth lecture in the representation series where we go through Steinberg's book. And today we're going to talk about what are called group actions and permutation representations. Logan, you'll notice that I have the correct pen this time. You're welcome. So throughout, I'm going to assume that all groups are finite and all actions are taken on finite sets. So groups are finite and actions on X, whatever. This is fine. No infinities. So I should first tell you what Steinberg means by a group action, which is a little different. Well, it's a special case of how it usually appears in the literature. The way it usually appears, an action is essentially equivalent to a representation. You know, for every action you get a representation. For every representation you can produce an action. But Steinberg restricts to homomorphisms between the group and symmetric group on X. So all of the bijections of X with itself. So we often, again, just like with a representation for sigma of G, we'll just write sigma G. Why do we want to do this? Because, well, this bijection acts on the set X, right? So if I give this thing an X to avoid writing multiple parentheses like this, I can just write like this. Okay, so the cardinality of X is called the degree of the action. So in our representation picture, the degree is the dimension of the vector space that the resulting map acts on. So here it's just the cardinality of the set, or the number of elements in the set, since we're assuming it's finite. So here's an example. We take lambda from G to the set of all bijections on G, defined by lambda G of X is G times X, right? We can do this because X is an element of G, so we can multiply two elements of G. So the action here is essentially just left multiplication and is called the, well, let me add the word left here, left regular action of G on itself. Okay, so a subset Y and X is called G invariant if sigma G of Y is contained in Y. That's for all Y in the set Y and G in the group. So there's a parallel here, again, between the action picture and the representation picture, right? For the representation, we care about G invariant subspaces. In this case, we care about G invariant subsets. Okay. Also, notice the dependence, once again, on the action. So we call this thing G invariant, but a better name would be sigma G invariant because the invariance does depend on the action. Okay, but that's the name we're stuck with, so we'll go with that. Okay, so I apologize, there's going to be a few definitions to start, just because we have to define things to talk about them. So let sigma be an action. The orbit of some element x in the set X under the group G is a set given by well, you essentially just act on X with every element of G. And the resulting set is called the orbit. Okay, so notice that the orbits are G invariant. Because if I take any element, let's call it, so if I take an element of the orbit, well, what does it look like? It looks like sigma h of x for some h and g. And if I want to act on this by any old element of the group, well, I'm assuming that sigma is a homomorphism. So this is equivalent to sigma gh of x. And gh is, of course, an element of the group. And so this must be in the orbit. So the orbit itself is G invariant. Another nice property that the orbits have is the orbits partition the set X. What do I mean by this? I mean that the union of all the orbits is the set X, and moreover, the orbits are disjoint from each other. So if I have an element that's sitting in one orbit and I have another element sitting in another orbit, either the orbits, so if the orbits are different, then these elements must be distinct. Okay, so how do we show that? Well, let sigma g of x be in the orbit, and let x be not equal to some other element of the set. Let's call it y. If we do have that sigma g of x is in the orbit of y, well then there's an element h in g such that sigma g of x is equal to sigma h of y because it's in the orbit corresponding to y. That's the definition of the orbit. Okay, but then that implies that x is equal to sigma g inverse of sigma h of y, which then implies that x is in the orbit of y, right? We again use the homomorphism property here. So that means that the orbit of x is then a subset of the orbit of y. So this is under the assumption that the element of the orbit of x is inside the element of the orbit of y. So on the other hand, uh-oh. Okay. So let me pull this up again.
You froze and we missed a bit of what you just said.
Okay, no worries. Does this look familiar?
Yeah, it was sigma g of x element of g y, I think.
Gx, gy. Yeah, so since if we assume that this an element of this orbit is inside of this orbit, then just by doing some manipulations, we can show that this orbit is in fact a subset of that orbit. And we can go the other direction as well. So moreover, this is not good. Okay. I'm going to try to continue. I don't know what's going on with our internet, but I'll keep going.
Um, I'll disconnect to like give you more bandwidth.
Yeah, that sounds good. Okay, sorry about that. Let's hope this stays online. Okay, so we can also get the other direction to show that these things are equal. The way we do that is y, under this assumption, is going to be equal to sigma h inverse of sigma g of x, which implies that y is in the orbit of x. Again, the homomorphism property is the in-between step here. And so putting that together, we have that the orbits are equal. Okay, so if x is not equal to y, so this means that for x not equal to y, either the orbit of x is equal to the orbit of y, or the orbits have empty intersection. Okay, so the point is that these orbits partition the set X. So obviously, I didn't show that the union is equal to X, but obviously if X is in, since X is in the orbit of X, right, you just take the identity element, multiply it by X, then X must be in there. Okay. Then unioning up all of these things will obviously give you X, right? So that completes the proof. Okay, so the point is that these orbits partition the set X, and that is a nice property for us to have. So there is an especially nice type of action which has only one orbit. In this case, it's called transitive. So another way to write that is for all x, y, and x, there's a g in g such that sigma g of x is equal to y. So, an equivalent way of expressing this is that the action is transitive if there's only one orbit. So all elements are connected by the action of a group element. Here's an example. This one's called the coset action. Let H be a subgroup of G, and define the action sigma from G to S G mod H, given by sigma G of X H equals GX H. Okay, so first of all, this G mod H here is not necessarily a group, right? But we don't require this thing to be a group anyway. It just has to be a set. We can always take the set of cosets, right? That's what this is. This is all cosets GH. And we don't need this to be a group. This is only a group when H is normal, but we don't care. Okay, but we can still define this action on this set here, given by left multiplication. So this action is transitive. So how do we see that? Well, we can just compute the orbit of the identity. So the identity in the set of cosets. Well, I shouldn't say the identity because it's just a set. But this element of the coset is, well, sigma g of 1h such that g is in G. Let's unpack this. This is just G times H such that G is in G. And this is none other than the set of all cosets. So we've shown that there's only one orbit, right? We know that these things partition the set, so any other orbit will be equivalent to this one. Okay, so that shows that this action is transitive. So Steinberg actually talks about an even stronger property than transitivity called two-transitivity. So let me define that. Action sigma of G on X is two transitive if given any two pairs of distinct elements. We need distinct elements x, y, and x, and distinct elements x prime, y prime, and x. So to be abundantly clear, x is distinct from y, x prime is distinct from y prime. There exists a G, just a single G, such that sigma G of X is X prime, and sigma G of Y is Y prime. Okay, so if you're anything like me, you would look at this definition and go, why in the world would you want to introduce this concept? But it turns out that this notion is equivalent to several conditions I think we'll talk about later on. Okay, so as an example, the identity homomorphism that sends the symmetric group to itself. So this is an action of Sn. So this is an action of Sn on the set 1 through n. Well, I claim that this action is actually two transitive. So to see this, let I be different from J and K be different from L. These are our two distinct pairs. What we need to do is we need to find a tau in Sn such that tau of I is K and tau of J is L. Well, we can let X be the set 1 through n minus ij. So whatever I and j are, just pull them out of the set. And similarly, we can let Y be 1 through n minus KL. That way, the order of X is equal to the order of Y. or the cardinality, if you like. They have the same number of elements. And we showed in the very first lecture that this implies that there exists a bijection from X to Y. So how do we define tau? Well, tau needs to itself be a bijection. It needs to exist inside of the symmetric group. So we define tau of, use another letter, let's use M, to be K if M is equal to I. That way we satisfy this condition. We want it to be L if M is equal to J. That way we satisfy this condition. And otherwise, well, we'll just take it to be alpha M. Okay. And so this thing is a bijection of 1 through n with itself. And it satisfies the two properties that we wanted. And so that implies that this identity action is two transitive. Okay, so hopefully that gives you an idea of what it means to be two transitive. Examples are always nice. All right, so let's move on. Lots of definitions today. Let sigma from G to Sx be a transitive group action. So we're assuming this thing is transitive, means it has only one orbit, or every element is connected by, or every two elements are connected by the action of a group element. And we could define another map. We'll call it sigma 2 in the subscript, sorry, the superscript, from G to S x cross x. This x is the same x as here. And we'll define it by sigma G2 acting on x1, x2 is just sigma G of x1, sigma G of x2. Okay. An orbit of sigma 2 is called orbital. That's very confusing, but that's the definition. Okay, so an orbit of sigma 2 is called an orbital. It's called an orbital of sigma. The number of orbitals is called the rank of sigma. Okay, so sigma itself has orbits. These are just the sets of these are the sets G, the entire group G acting on some element X. Sigma 2 is also an action, but it's an action on X cross X. And so it has its own orbital, sorry, its own orbits. And those orbits are called orbitals of sigma. It's very stupid. But anyway, the number of orbitals is called the rank of sigma. Okay, so notice that delta, which is the set of all of these, well, you might call them diagonal elements. This is an orbital for any transitive group action. That transitive property is important. So why is this the case? Well, for x, y, and x, there is a g in G such that y, the element y, which remember is in delta, is equal to sigma g of x, sigma g of x, which is sigma g2 of x, x. So why do we have this property? Because we're assuming that the action is transitive. So sigma itself is transitive, right? So I'm calling that sigma. Okay, so this implies that this diagonal set is an orbital. Why? Because it's an orbit of sigma 2. Okay, so delta is either called the diagonal or the trivial orbit. Sorry, trivial orbital. I'm going to keep making that mistake. Okay. So just as an aside, orbitals are pretty closely related to graph theory. So if G acts transitively on X, which is going to be the assumption most of the time here, then any non-trivial orbital can be viewed as the edge set of a graph with vertex set X. Right? So the edge set is the set of all the edges, right? That's why we have pairs here. The group G acts on the resulting graph as a vertex transitive group of automorphisms. So these bijections are automorphisms of the graph. Okay. So that's one place you might consider studying this sigma 2 function. Okay, so let's finally start proving some stuff. Okay, so I'm going to assume from now on that sigma from G to Sx is a group action. And I will tell you if it's transitive or not. Okay, so for now, we're only assuming it's a group action. And I'm also going to assume from now on that the cardinality of x is greater than or equal to 2. A lot of this still holds for the cardinality of x being 1, but it's a very trivial case most of the time. And I think I have it in my notes to specify whenever something needs this restriction. Okay, so sigma is 2 transitive if and only if sigma is transitive and the rank of sigma is 2. So the rank of sigma, remember, is the number of orbitals of sigma, which is the number of orbits of sigma 2. Okay, so proof. So first, we can observe that transitivity is necessary for 2 transitivity, because if G is 2 transitive on X and X, Y are in X, then we can choose an X prime not equal to X and a Y prime not equal to Y. And by 2 transitivity, so such that there exists a G in G with sigma G of X equal to Y and sigma G of X prime equal to y prime. So this shows that sigma is transitive, right? Because we've, for any two elements, we've exhibited a group element that connects them. This other stuff here is just padding so that we can use two transitivity. We don't really care what these things are. Okay, so that's proof that two transitivity is stronger than transitivity. So if you have two transitivity, then you also have transitivity. So next, observe that x cross x minus delta. So this is just the set of all pairs such that x is not equal to y. This is an orbital. If and only if. For any pairs x not equal to y and x prime not equal to y prime, there exists a g in G with sigma g of x equal to x prime and sigma g of y equal to y prime. So this thing is an orbital if and only if. Okay, that's getting annoying. All right, so where was I? This thing here is an orbital if and only if you can find, well, for any pairs, x not equal to y and x prime not equal to y prime, we can connect these pairs with a single group element. That's what it means to be an orbit of sigma 2, which is what it means to be an orbital of sigma, right? And so we have that it's an orbital if and only if this property holds, which is exactly that sigma is two transitive. Okay. So I think we're going to use that again later. So we have this proposition tells us two transitivity is equivalent to being transitive and having a rank of 2. All right. So given a group action, so we'll continue to call it sigma, we can compose it with the standard representation. That's the representation we got from applying the permutation to the rows of a matrix, of the identity matrix. And we can compose these to obtain a representation. Representation sigma tilde, which maps from G to GL, and I'm going to introduce this notation Steinberg uses. So this complex numbers, bold C, written to the left of X, just means the span of X over the complex numbers. Oops. Okay, so the representation defined by sigma tilde G. So now this acts on the span of X over C. So that's all formal linear combinations of elements of X. Let's just pick one. And the way we define this is by using sigma, not sigma tilde, using sigma to act on each individual x. So it's linear by assumption. And one way to rewrite this is as the sum over x and x of c sigma g inverse of y. So you do this by doing a substitution. Okay, so this is called the permutation representation. Associated to sigma. Okay, so note.
Yeah, sorry to interrupt,
Go for it.
but should it be a y in the index of the second summation?
Yes, thank you.
Cool.
So note that the degree of sigma tilde, so sigma tilde as a representation, is equal to the degree of sigma, which is a group action, right? So the dimension of the vector space sigma tilde acts on, so the dimension of all the formal linear combinations here is equivalent to the cardinality of the set X, right? And that makes sense because a basis for this space is just all the elements X, all the elements inside X. Okay. So let lambda be the regular action. So that was that left multiplication action. So that's supposed to be a G. Then lambda tilde, the permutation representation, is the regular representation, which is why this is called the regular action. Okay. So I want to prove another proposition here, which just says that this permutation representation is always unitary. So again, group action, then the permutation representation, sigma tilde, which remember goes from G to the general linear group on the span of X, so all formal linear combinations of elements of X. This is a unitary representation. We're going to get through this, guys. Okay, so as I was saying, I want to prove this proposition that just says that the permutation representation is in fact a unitary representation of G. Okay, and the proof is really simple. You just do the calculation. Sigma G tilde acting on some element of the span of X. And another element. We take the inner product, and we want to make sure that the inner product is the same as if I had taken the inner product without applying sigma G tilde. Well, the definition of this guy, remember we can write this as the sum over X and X of C G inverse of X, X, and the sum over Y and X of DG inverse of Y, Y. And this inner product is the sum over x and x of CG inverse of x DG inverse of x complex conjugate. And this is equal to this guy by a substitution. Okay. And then finally, this is just the inner product of x. The first formal sum with the second formal sum. And so the representation must be unitary. Okay. So first step was the definition of the action or of the representation. Second step, we just did the inner product. Third step was the substitution. And then finally, we recognize that as the inner product. Okay, so permutation representation, always unitary. Good. Okay, so given an action, the character of this permutation representation is something that we'd really like to know. I did not seem to write down the definition of this guy. Okay. Yes. Make sure I get it right. Okay. So we can define a set fix G by a set of x in x such that sigma G of x is equal to x. So it's all the elements of x which are fixed by this group element G. And I'm missing a proposition. I guess I skipped over it in my notes, but okay. I'll just tell you what it is, and the proof is like 3 lines long. So I'll refer you to the book so I don't have to sit here and hold this. So fix 2 of G is the set of fixed points of G on x cross x. Some more space. Let's write it down here. The points x, y, and x cross x such that sigma G2 of xy is just equal to xy. And there's a proposition, I'll just state it as a fact, it's in Steinberg's book, it's 2 or 3 lines long, but it says that fix 2 of G is equal to fix of G cross fix of G. Okay. So we have a proposition now. We want to know something about the character of this permutation representation, because the character carries all the information about the representation. So it turns out that this is exactly equal to the cardinality of this set fix G. Okay, so here's the proof. Let x be x1 through xn, and let a square brace denote the matrix of sigma g tilde. So denote the matrix. Sigma g tilde with respect. I have to specify the basis. The basis I'm going to choose is the obvious one, x. Then sigma g tilde of a basis element. Let's use j actually. Let's use j. Is equal to sigma g of xj. So notice no tilde here. Why is that the case? Because the way this representation is defined is by its action on the basis elements. Right? We defined it so that sigma, I'll write it again here, sigma tilde g of a sum is just the sum with sigma g acting on x. So xj is one of these basis elements, so we're basically just setting the constant equal to 0 except for xj. All right, so this means that sigma g tilde ij is 1 if xi is equal to sigma g of xj and 0 otherwise. In particular, the II coefficients, so the diagonal coefficients, are 1 if xi is sigma g of xi and 0 otherwise. I have two equal signs. And this is the same as saying that it's equal to 1 if xi is in the fixed set and 0 otherwise. And so what does this mean? Well, the character of sigma tilde of g. So remember that this is the trace of sigma g tilde, and the trace is the sum of the diagonal elements. So we get a 1 every time x is in the fixed set. And so this is just the cardinality of the fixed set. And that completes the proof. All right, so we've defined this permutation representation. We know it's unitary. And moreover, we know exactly what the character is. Well, it still depends on G, right? We still have that G dependence, but we know that it's this very nice set. Okay, good. So like the regular representation, so remember we studied that one a while back, I think chapter 4 or 5. And the nice thing about the regular representation was that although it wasn't it wasn't irreducible, it had a copy of all the irreducible representations in its decomposition. So like the regular representation, the permutation representation will also not be irreducible. It'll be reducible whenever the cardinality of x is greater than 1. But it still has some nice properties, like the regular representation. Okay. So first, let me define something. Let phi be a representation, not necessarily the permutation representation. Then Vg, which is the set of all V in this vector space V, such that phi g of V is V for all G in G. is the fixed subspace of G. Okay. So I've had this space come up in some papers of mine. I've always called it the G-symmetric subspace, but you'll see it written that way, I think, in the quantum information literature. But okay, so Steinberg calls this the fixed subspace, and I have a note from Marguerite in my notes saying that this is the G-symmetric subspace, but she's not here, but she can't be. Okay, anyway, it is easily verified that VG is a G invariant subspace. Right? How do we verify that? Well, take some element in this subspace, call it V, right? What happens when you apply any old phi G to it? Well, it's just V again. So of course it's still in the subspace. Okay. And the subrepresentation phi restricted to VG is equivalent to the dimension of VG copies of the trivial representation. So the trivial representation is the representation where what's the one-dimensional representation? Everything is mapped to one. Okay. So maybe I should give some argument for this. So first I want to say, remember that if you have a representation phi and you have a G invariant subspace, you can produce a new representation, as which we usually call a subrepresentation, by restricting the original one to that invariant subspace. Right? And this only works because this thing is an invariant subspace. Right? If we apply phi G to an element of this thing, then it's still inside of this subspace. And that's the property we need to have in order to have a representation. So how do we see that this thing is equivalent to trivial representation or copies of the trivial representation? Well, remember the matrix of this guy applied to G is the identity, that's the trivial representation on VG. So why is it the identity? Well, because if I apply phi G to an element of VG, it does nothing. That's the identity transformation. So the character is the dimension of VG, which is the dimension of VG times chi1, which is essentially just 1. So this tells us that this subrepresentation is just several copies of this trivial representation. Okay. So I'm going to need some space for this next one. We are getting there. So again, let phi be a representation. It doesn't have to be the permutation representation. And let chi1 be the trivial character. So chi1 equals trivial character. That just means it's the character of the trivial representation, the one that maps everything to 1. Then we have that chi phi, so the character of phi, inner product with the character or the trivial character is equal to the dimension of this G-symmetric subspace or the fixed subspace, whatever you want to call it. Okay, proof. So we can write V as V1 direct sum M1 times through Vs, and we can direct sum that Ms times, where V1 through Vs are irreducible subspaces, sorry, irreducible G invariant subspaces. Whose associated subrepresentations range over the distinct equivalence classes of irreducible representations of G. Okay, so this is Match-Key's theorem. Right? We proved this a while back. Given a representation of a finite group, we can always decompose it. It's completely irreducible. We can always decompose it into a direct sum of irreducible representations. And I'm just letting these V1 through Vs be the subspaces. And the representations I'm going to call phi1 through phi s as usual. So without loss of generality, we can assume that V1 is, or I should say phi1 is equivalent to the trivial representation. So we're assuming that the cardinality of x is greater than or equal to 2, and a consequence of that is that this representation is going to contain a copy of the trivial representation. So let's just let phi1 be that copy. Okay, so I should clarify, well, phi I, remember, is the same thing as phi restricted to vi. That should be in the subscript. If v is an element of v, then we can write v as a sum of v1 through vs with vi contained in vi direct sum with itself mi times. And phi g of v is equal to, well, this is phi1 direct sum with itself, yes, this thing acting on v1. So there's well, there's m1 copies here. And phi s there are ms copies here. Okay. But this thing, so we're assuming that phi1 is the trivial representation, and so this whole thing here is going to be equal to v1, right? Trivial representation max g to 1. So what that means is that if well, g is in, g, that doesn't make any sense. See what I want to say here. Okay, yeah, this is a typo in Steinberg. So I'll write it down and maybe we can try to decode what he meant. So he says that G is in VG, which makes no sense, right? The element of the group can't be an element of the fixed subspace. If and only if VI is in VIG direct sum with itself MI times for all Q less than or equal to I less than or equal to S. Okay, so G is in VG if and only if VI is in VIG direct sum MI times. Okay, so if this is the case, then the rest of these will produce just VI. Okay, this should be a V. So if each VI is in the fixed subspace, then the representations will act trivially on that VI, right? And so we'll be left with the sum of V1 through Vs. And that's just V. When that's the case, that means phi G on V is equal to V, and so V is in the fixed subspace. Conversely, if V is in the fixed subspace, then we can show that VI must be in the individual fixed subspaces. I don't immediately see that actually. Okay, I want to get to some other things, so I'm gonna take that for granted for now. Okay, maybe we can talk about it after. So in other words, VG will be equal to V1 direct sum M1 times plus V2G direct sum M2, and we keep going up to VSG direct sum MS times. So the fixed subspace of V is given by the direct sum of the fixed subspaces of VI. The fixed subspace of V1 will just be V1. Okay, let's let I be greater than or equal to 2, since VI is irreducible and not equivalent to the trivial representation. We've already assumed that V1 is the trivial representation, so all those copies are counted with the parameter M1. And VIG is G invariant, just by definition. It follows that VIG is equal to 0. This is Schur's lemma. This is an application of Schur's lemma. We see it pop up again here. Thus, VG is V1 direct sum with itself. This is M1 times, and so chi phi chi1 is equal to the dimension of VG. Because this M1 is the number of copies of the trivial representation. which is what this inner product will give you. And so that completes the proof. Okay. So we are in the process of studying the permutation representation, and we have this proposition that's going to help us later on that tells us that the number of copies of the trivial representation in any old representation is given by the dimension of the fixed subspace corresponding to that representation. So let's let sigma be a group action again. And we'll let O1 through OM be the orbits of G on X, and define VI to be the sum over all the X and the ith orbit. Then V1 through VM is a basis for the span of X. Well, span X is the fixed subspace of that, and hence the dimension of that space is the number of orbits of G on X. So how many vectors are here? The number of vectors is the number of orbits. Yeah. So you can see it from the definition here. And so if that's a basis, well then the length of the basis is the number of orbits of G on X. And if it's a basis for this space, well then the dimension is equal to that. Okay, so let's prove this. So first observe that sigma G tilde acting on VI, so the ith basis element, is the sum over X in OI, so the ith orbit. And we're summing sigma G of X. And another way to write this is the sum over Y in the orbit, the ith orbit. We're summing Y, which is VI. So this follows from the fact that sigma G, all it does is it permutes the elements of the orbit OI. So remember, sigma G is a bijection. And so this allows us to do a substitution and the trick where we know that if X ranges over every element of the orbit, then sigma G inverse of X will also do that. Okay, so it's a substitution. So V1 through VM are in the span of X, or sorry, the fixed subspace of the span of X. And since the orbits are disjoint, we have the inner product of VI with VJ is equal to the number of elements in the ith orbit if I is equal to J and 0 otherwise. And so V1 through V, I wrote S here. I think I want an M. Yeah, let's just use M. Is an orthogonal set. Of non-zero vectors. But this implies that they're linearly independent. Remember, orthogonal vectors are linearly independent. Okay, so now we just have to show that they span the fixed subspace of the span of X. Okay. So suppose that V is some element of this space. If Z is in the orbit corresponding to Y, so we say maybe Z is sigma G of Y, well then we have that the sum over X and X, Cx, X, so this is V, that's just definition, and this is equal to sigma G tilde of V, because V is in the fixed subspace, which is equal to the sum over X and X, Cx sigma G of X. Definition of sigma G tilde. And this implies, by comparing the basis elements on each side, remember we can rewrite this as the sum over Y and X of sigma G inverse of Y, Y. So by comparing the basis elements on each side, we see that CZ is equal to CY. Okay. So that means that there exists constants C1 through Cm such that Cx is Ci for all x in the ith orbital, and V is equal to the sum over X and X. So that's just the definition. This will be equal to the sum from I equals 1 to M, and the sum over the elements of the orbital, Cx(x), which is just the sum from I equals 1 to M, Ci, sum over the elements in the orbital. But this thing is just Vi. So that's and so that gives us that this list of vectors will span the fixed subspace of the span of X. And so that completes the proof. Okay, so recap. We gave an explicit basis for the fixed subspace of this span of X. It's just the sum of the elements of each orbital. And so that implies that the dimension of that space is equal to, well, the number of orbitals, because how many vectors are there? Well, it's just the number of orbitals. I keep saying orbitals, I mean orbits. Okay. Okay, so of course, G always has at least one orbit on X. So the trivial representation must appear as a constituent of the permutation representation at least once. And we have that sigma tilde is in fact not irreducible. Because we're assuming here that the cardinality of X is greater than 1, remember. And now that brings us to a nice corollary of this result, which is Burnside's lemma. So this is a very nice lemma used all the time in combinatorics. If sigma is an action of G on some set X, So let this be a group action, not necessarily transitive. And let M be the number of orbits of G on X. That means it's the dimension of the fixed subspace of the span of. Hopefully that's the last time. This is terrible. Okay, so I'm doing Bernstein's lemma now. We let sigma be a group action, and we let M be the number of orbits of G on X. What does that mean? Well, by our previous proposition, that means that the dimension, that M is the dimension of the fixed subspace of the span of X. That's what we just proved. Well, then Bernstein's lemma says that M is exactly 1 over the order of G times the sum over the elements of G of the cardinalities of the fixed sets. And now here is the very simple proof. M is the inner product of the character of the permutation representation with chi1. So why is that the case? Well, this is the degree, or so it's the number of trivial representations. And we showed that that was equal to, let's see if I can pull it back up. Yes, here we go. We showed that that was equal to the dimension of the fixed subspace of the vector space of the representation. Now, the proposition after that, if I have it right here, shows that the dimension of that space is precisely equal to the number of orbits of G on X. And so that's how I'm getting this first equality here. Okay, and now this is equal to, just by the definition of the inner product, chi sigma tilde of G, chi1 of G, complex conjugate. But the trivial representation is equal to 1. Or the trivial character is equal to 1. And so this is 1 over the order of G, sum over G and G. And we showed earlier that this character was equal to the cardinality of the fixed set. So I used 3 propositions that we previously proved here. And that proves Bernstein's lemma. Okay, all right. So here's the exciting thing for me. Bernstein's lemma you can use to prove what's called Poy's numeration theorem. So let me write that one out. So the fact that you can get Bernstein's lemma from representation theory means that if Bernstein's lemma is used to prove Poy's numeration theorem, then you get Poy's numeration theorem from representation theory. And I think that is just wonderful. Okay, so if G is a finite group, X is a set of just objects, yeah, some elements. So X is a set, I should really say. And Y is a set of colors. So mathematically X and Y are just sets. The group G acts on the set Y X of colorings F from X to Y. So how does it do that? Well, F, for every object in X, F assigns a color. So once you have an assignment of all the colorings, we'll just permute them according to the representation. Sorry, not the representation. Permute them according to the element of the group. So the colorings are considered equivalent if they lie in the same orbit. So think about what that means physically. If I have a necklace with N beads on it, and I want to color each bead, right? So the beads are the set X, and the colors are the set Y, and F is just the map that takes each bead and assigns it a color. Then the way that G acts on this coloring is by rotating the necklace, for example. Right? So G there would be the cyclic group. You could do the dihedral group, which allows reflections. That's like flipping the necklace around. Yeah. But the point is that if two colorings are connected by this rotation of the necklace, then they're considered equivalent, right? You know, if I color my necklace and I throw it in the air or whatever, and it comes back down, whatever coloring it lands on, I want that to be equivalent. Okay, so that's the motivation for having them lie in the same orbit, right? Being in the same orbit just means that there's a group element connecting them. Okay, then the number of n-equivalent colorings is 1 over the order of G, the sum over G and G. So this is Burnside's lemma, right? It's the number of orbits. And that's 1 over the order of G, the sum over G and G, the order of Y, so the number of colorings raised to the C of G power. And this is where the order of Y is the number of colorings. Sorry, the number of colors, I should say. And C of G is the number of cycles in the permutation representation of G. So why is this the case? So a coloring will fix G, or G will fix a coloring. Yeah, G will fix a coloring if how do I explain this? Okay, so how many colorings, or how many possible maps are there from Y to X? Well, it's Y to the order of Y to the order of X, right? But I want to exclude ones that are colorings that are equivalent to each other, right? So all I need for a valid n-equivalent coloring is for the map to be constant on a cycle. Right? So if I have the permutation 1, 2, 3, 4, 5, right? I want this to fix my coloring, and so I just have to define F so that F of 1 is equivalent to F of 2 is equivalent to F of 3, and F of 4 is equivalent to F of 5. How many functions are there like that? Well, it's the number of colorings to the number of cycles power, right? The number of cycles here is 2. Okay. So that's how I get this, and this thing is exactly equal to the cycle index polynomial of the group G with the the number of colors plugged in everywhere. So Christoph, you will recognize this hopefully from our dubious identities paper.
Yep.
Okay. All right. So that was my favorite part of this section. I think it's a nice little result. But we can go even further. So if sigma is a transitive group action, then the following equalities hold. The rank of sigma is 1 over the order of G, the sum over G and G, fix. That should be a lowercase g squared, which is the inner product of chi sigma tilde with itself. So proof is not bad. So remember the rank of sigma is the number of orbits of sigma 2 on x cross x. And the number of fixed points of G on x cross x is, so this is one of the things I quoted earlier from Steinberg but didn't prove. The first equality follows from Burnside's lemma. Now the second, we just have to do the computation. So the definition is so, right? This follows from the proposition we had where chi sigma tilde was equal to the cardinality of the fixed set. And this is exactly what we wanted. Okay, so we have a nice formula for the rank, and remember that we had this result a while back that said that a representation was irreducible if and only if the inner product of the characters, the character with itself was equal to 1, right? And so that relates the irreducibility of the permutation representation with the rank of the action that it comes from. Okay. Let me see how much more of this I want to do. Okay. All right. So I think that I will go ahead and stop there for now. That is absolutely plenty. I'll see if I want to do any more of this next time or move on to the next chapter. But any questions? Any questions off the record, Christoph?
Off the record.
Wait, hang on. Did I?